When tightening a lock nut against a painted electrical box, the mechanical force exerted crushes the paint between the lock nut and the box's surface. This crushing action creates a direct metal-to-metal contact. This metal-to-metal contact serves as the foundation for a solid ground path. You can verify the effectiveness of this grounding method through a simple test using a multimeter. By measuring the resistance between the lock nut and the surface of the electrical box, you can assess the quality of the electrical connection. A very low resistance reading will indicate a strong and reliable electrical connection, confirming that the paint has been effectively displaced to establish the necessary metal-to-metal contact for grounding. Electrical grounding is a critical aspect of electrical safety and ensuring the proper operation of electrical systems. Grounding provides a low impedance path for fault currents, which helps to protect people and equipment from electrical shock and damage. In electrical systems, the ground is a conducting connection, whether intentional or accidental, between an electrical circuit or equipment and the earth, or some conducting body that serves in place of the earth. Grounding ensures that if a fault occurs, such as a short circuit, the current will flow safely to ground, tripping a circuit breaker or fuse and disconnecting the power supply. The National Electrical Code, (ONIC), provides comprehensive guidelines for electrical grounding to safeguard electrical installations and prevent hazards. There are several reasons why proper grounding is essential. Firstly, it protects against electrical shock. If a live wire comes into contact with the metal chassis of an appliance or piece of equipment, a person touching the equipment could receive a dangerous electrical shock. A proper ground provides a low resistance path for the fault current, causing the circuit breaker to trip quickly and preventing the shock. Secondly, grounding prevents the buildup of static electricity. Static electricity can accumulate on non-conducting surfaces, such as carpets or clothing, and discharge suddenly, causing a shock or potentially igniting flammable materials. Grounding helps to dissipate static electricity safely. Thirdly, grounding reduces electromagnetic interference. Electrical equipment can generate electromagnetic interference, which can disrupt the operation of other electronic devices. Grounding helps to contain and reduce this interference. Fourthly, grounding improves the reliability of electrical systems. By providing a stable reference point for voltage, grounding helps to ensure that electrical equipment operates correctly and reliably. In electrical installations, there are two main types of grounding systems: system grounding and equipment grounding. System grounding involves grounding the neutral conductor of the electrical system, typically at the service entrance. This helps to stabilize the voltage and provide a return path for fault currents. Equipment grounding involves grounding the metal enclosures of electrical equipment, such as appliances, machinery, and electrical boxes. This provides a low impedance path for fault currents, protecting people from electrical shock. The NEC specifies the requirements for grounding different types of electrical systems and equipment. These requirements vary depending on the voltage, type of equipment, and the specific application. Some of the key requirements include the size of grounding conductors, the methods for connecting grounding conductors to equipment, and the location of grounding electrodes. Grounding electrodes are conductive rods, plates, or other devices that are buried in the earth to provide a connection to ground. The NEC specifies the types of grounding electrodes that are permitted, as well as the requirements for their installation. The most common types of grounding electrodes are ground rods, metal water pipes, and concrete encased electrodes, also known as UFRs. Ground rods must be at least 8 feet long and driven into the ground so that at least 8 feet of the rod is in contact with the soil. Metal water pipes can be used as grounding electrodes if they are in direct contact with the earth for at least 10 feet. Concrete encased electrodes must be at least 20 feet long and encased in at least 2 inches of concrete. The NEC also requires that grounding systems be tested to ensure that they are effective. Ground resistance testing involves measuring the resistance between the grounding electrode and the earth. A low resistance reading indicates a good connection to ground. If the ground resistance is too high, it may be necessary to install additional grounding electrodes or improve the existing grounding system. In addition to the NEC requirements, there are also industry standards and best practices for electrical grounding. These standards provide more detailed guidance on how to design, install, and maintain effective grounding systems. The Institute of Electrical and Electronics Engineers, or IEE, publishes several standards on grounding, including IEE Standard 142, also known as the Green Book, which provides recommendations for grounding and bonding of electrical systems. Proper grounding is essential for electrical safety and equipment protection. By following the NEC requirements and industry best practices, you can ensure that your electrical system is properly grounded and that people and equipment are protected from electrical hazards. When dealing with locknuts and painted enclosures, it's important to understand how grounding is achieved through mechanical connections. The primary concern is establishing a reliable electrical path despite the presence of paint, which is an insulator. When a locknut is tightened against a painted surface, the force applied causes the paint to be crushed or displaced, creating points of metal-to-metal contact. These contact points, while seemingly small, can provide a sufficient path for grounding, especially when multiple contact points are established around the circumference of the locknut. However, the effectiveness of this grounding method depends on several factors. Firstly, the thickness and type of paint. Thicker layers of paint or certain types of paint may be more resistant to being crushed or displaced, potentially hindering the establishment of a good electrical connection. Secondly, the tightness of the locknut. Insufficient tightening may not create enough pressure to effectively break through the paint layer. Thirdly, the surface condition of the enclosure and locknut. Corrosion or other surface contaminants can impede electrical conductivity. To ensure a reliable ground connection, it's crucial to verify the continuity between the locknut and the enclosure using a multimeter. A low resistance measurement, ideally less than 1 ohm, indicates a good electrical connection. If the resistance is higher, it may be necessary to further tighten the locknut or remove more paint to improve the connection. In situations where a painted enclosure is used, it's generally recommended to remove the paint from the area where the locknut will make contact. This ensures a direct metal-to-metal connection and a more reliable ground path. This can be done by scraping, sanding, or using a wire brush to remove the paint. Another approach is to use grounding locknuts, which are specifically designed with teeth or serrations that bite through the paint to establish a good electrical connection. These locknuts are often used in applications where it's difficult or impractical to remove the paint from the enclosure. The NEC provides guidelines for grounding electrical equipment and enclosures. Section 250.96 covers the requirements for bonding metal enclosures and raceways. It states that metal enclosures and raceways must be bonded together to form a continuous electrical path. This bonding ensures that fault currents can flow safely to ground, tripping a circuit breaker or fuse and preventing electrical shock. Section 250.92 specifies the methods for bonding metal enclosures and raceways. It allows for the use of various bonding methods, including bonding jumpers, bonding screws, and listed fittings. Bonding jumpers are conductors that are used to connect two or more metal enclosures or raceways together. Bonding screws are screws that are specifically designed to provide a low-resistance connection between metal parts. Listed fittings are fittings that have been tested and certified by a recognized testing laboratory to meet specific safety standards. When using locknuts for grounding, it's important to ensure that they are properly tightened and that they make good electrical contact with the enclosure. If the enclosure is painted, it may be necessary to remove the paint from the area where the locknut will make contact. It's also a good practice to use a style washer or other type of serrated washer between the locknut and the enclosure to improve the electrical connection. In addition to the NEC requirements, there are also industry standards and best practices for grounding electrical equipment and enclosures. These standards provide more detailed guidance on how to design, install, and maintain effective grounding systems. The IEE publishes several standards on grounding, including IEE Standard 142, also known as the Green Book, which provides recommendations for grounding and bonding of electrical systems. In summary, when dealing with locknuts and painted enclosures, it's essential to ensure that a reliable electrical connection is established for grounding purposes. This can be achieved by removing the paint from the contact area using grounding locknuts, and verifying the continuity of the connection with a multimeter. Following the NEC requirements and industry best practices will help to ensure that electrical systems are properly grounded and that people and equipment are protected from electrical hazards. The principles of electrical grounding are rooted in physics and electrical engineering. The fundamental concept is to provide a low impedance path for electrical current to flow back to the source in the event of a fault. This low impedance path allows a large amount of current to flow, which will quickly trip a circuit breaker or fuse, disconnecting the power and preventing electrical shock or damage. The impedance of a grounding path is determined by several factors, including the resistance of the conductors, the inductance of the circuit, and the capacitance of the circuit. Resistance is the opposition to the flow of current, and it is measured in ohms. Inductance is the property of a circuit that opposes changes in current, and it is measured in henries. Capacitance is the ability of a circuit to store electrical charge, and it is measured in farads. In a grounding system, the goal is to minimize the impedance of the grounding path so that fault currents can flow quickly and safely to ground. This is achieved by using low-resistance conductors, minimizing the length of the grounding conductors, and avoiding sharp bends in the grounding conductors. The NEC provides specific requirements for the size and type of grounding conductors that must be used in electrical installations. These requirements are based on the size of the circuit and the type of equipment being grounded. The NEC also specifies the methods for connecting grounding conductors to equipment and enclosures. These methods are designed to ensure that a reliable electrical connection is established. In addition to the NEC requirements, there are also industry standards and best practices for grounding electrical systems. These standards provide more detailed guidance on how to design, install, and maintain effective grounding systems. The IEE publishes several standards on grounding, including IEE Standard 142, also known as the Green Book, which provides recommendations for grounding and bonding of electrical systems. Understanding the principles of electrical grounding is essential for anyone who works with electrical systems. By following the NEC requirements and industry best practices, you can ensure that electrical systems are properly grounded and that people and equipment are protected from electrical hazards. When working with Locknuts and painted enclosures, it's important to be aware of the potential for the paint to interfere with the grounding connection. Paint is an insulator, and it can prevent a good electrical connection from being established between the locknut and the enclosure. To overcome this issue, it's generally recommended to remove the paint from the area where the locknut will make contact. This can be done by scraping, sanding, or using a wire brush. Another option is to use grounding locknuts, which are specifically designed with teeth or serrations that bite through the paint to establish a good electrical connection. When installing locknuts, it's important to tighten them properly to ensure that they make good electrical contact with the enclosure. The NEC requires that locknuts be tightened to the manufacturer's specifications. If the manufacturer's specifications are not available, the locknuts should be tightened until they are snug and do not move easily. After the locknuts are installed, it's a good practice to test the grounding connection with a multimeter. This will verify that a good electrical connection has been established. To test the grounding connection, connect one lead of the multimeter to the locknut and the other lead to a non-good ground, such as a grounding electrode or a metal water pipe. The resistance reading should be very low, ideally less than 1 ohm. If the resistance reading is high, it indicates that there is a poor electrical connection and that the grounding needs to be improved. In summary, when working with Locknuts and painted enclosures, it's important to be aware of the potential for the paint to interfere with the grounding connection. To overcome this issue, it's generally recommended to remove the paint from the area where the locknut will make contact or to use grounding locknuts. It's also important to tighten the locknuts properly and to test the grounding connection with a multimeter to verify that a good electrical connection has been established. By following these steps, you can ensure that electrical systems are properly grounded and that people and equipment are protected from electrical hazards. The NEC specifies the minimum requirements for electrical installations, but it's always a good idea to go above and beyond these requirements to ensure the safety of people and equipment. For example, It's always a good idea to use high-quality grounding conductors and to install grounding electrodes that are larger than the minimum size required by the NEC. It's also a good idea to regularly inspect and test grounding systems to ensure that they are functioning properly. By taking these extra steps, you can help to ensure that electrical systems are safe and reliable. Electrical codes and standards are constantly evolving to reflect new technologies and best practices. It's important to stay up to date on the latest changes to the NEC and other relevant standards. This can be done by attending training courses, reading industry publications, and consulting with qualified electrical professionals. By staying informed about the latest changes to electrical codes and standards, you can help to ensure that electrical systems are installed and maintained in a safe and compliant manner. The topic of locknuts and grounding in painted enclosures highlights the importance of understanding the fundamental principles of electrical grounding and bonding. Grounding and bonding are essential for electrical safety and equipment protection, and it's important to follow the NEC requirements and industry best practices to ensure that electrical systems are properly grounded and bonded. When working with locknuts and painted enclosures, it's important to be aware of the potential for the paint to interfere with the grounding connection. To overcome this issue, it's generally recommended to remove the paint from the area where the locknut will make contact or to use grounding locknuts. It's also important to tighten the locknuts properly and to test the grounding connection with a multimeter to verify that a good electrical connection has been established. Electrical safety is everyone's responsibility. By following the NEC requirements and industry best practices, you can help to ensure that electrical systems are safe and that people and equipment are protected from electrical hazards. Always remember to de-energize electrical circuits before working on them and to use appropriate personal protective equipment, or PPE, such as gloves and safety glasses. If you are not qualified to work on electrical systems, it's best to hire a qualified electrical contractor. Working with electricity can be dangerous, and it's important to take the necessary precautions to protect yourself and others.